All right, no emails, no requests. And so, what I'm talking about, this is more for my edification than it is for yours. Right now, you got a discussion board on a Hess's Law problem. There's two ways to solve Hess's Law. I'm going to work through both of them, but again, I want to make this very clear. These are office hours, these are not lectures. I'm doing this because I actually kind of need to know the answer for the discussion board. And I figure if I've got to go through all the work anyway, I might as well make one video. Now, again, if you go to the course website under videos, there are already videos posted on how to do this. I would recommend you go to those. They're examples of what you're about to see in terms of the discussion board. There's very much going to be one of those on the exam. Already a student asked me, is like, well, we can't find DHDG, we'll be given values if we can't define DS. Yes. So you, on the next exam, you have a three-part problem in the free response. Find the delta H and the delta G of a reaction based on what you're seeing on the discussion board, and then take the delta H and the delta G and find the delta S. Well, if you can't find delta H and delta G, you can't really find the delta S. In the exam, will explicitly state that if you cannot find DG and delta G and delta H, sorry, not quite. If you can't find delta G and delta H on your own, you can use values that I will give you, but it's going to be at a penalty. And the penalty is half credit. And the reason why that penalty is there is that if you have delta H and delta G, you need to use those. And part of that problem is understanding how delta H and delta G fall into that problem solving technique. So I don't want you going, well, I have to find delta H, delta G. I just go right and use the problem, what the problem gives me. No. Prove that you know how to connect the dots between the delta G, the delta H, and the delta S. But if you aren't able to do the delta G, delta H, you can still find the delta S with the values I give you, but again, the penalty is more to encourage you to use your own values, not to rely on the values I'm giving you, because the values I give you are not the values for the delta H and the delta G. They're just dummy numbers to give you something to work with. But anyway, the discussion board. Hess's law represent really kind of the hard end of problems with regard to what's coming up on the exam. Now, I also said this upcoming exam is the hardest exam you're going to do this semester. So we have lead and sulfur going to lead to sulfide. The delta H of negative 96.6. We have lead sulfide plus oxygen going to oxygen, going to lead to sulfate. By the way, these are all real values. I didn't make any of these up. So we got these three reactions, and what we want to do is we want to figure out how much heat is released or gained from this reaction. Now, there are two approaches to this, and well, there's actually three approaches. So the first approach is adding and subtracting reactions. You probably actually saw this in Chem 1, depending on who you had. Hopefully they covered how to do very basic Hess's law reactions. Switch to delta G is the exact same procedure, but the thing is that we can add and subtract reactions. Now, why is this a bad way to do it? It is a bad way to do this because this is not at all how it's done in practice in the real world. You're not given a series of reactions and asked to manipulate them. This is a cool consequence of microscopic reversibility. It's a cool concept that can be tied to intermediate reactions, but ultimately this is not how you would ever do it, but whatever. We have to teach it because it has historically been taught and expected to be known. But in practice, what we're going to do for our second method is actually more akin to what's actually done. So, to add and subtract reactions, what we need to do is figure out what's on the correct side. So, first thing I do is I identify things that are in the final products or in the final reaction, and everything else that doesn't show up underlying green here, and everything that isn't in the final bit, that's going to be, let's see if I can move that so you can get the glare out of the way. helps it a little bit. Basically, anything that remains, anything that isn't underlined has to be eliminated. So the lead here is on the correct side and only appears on one side. So odds are we're adding this reaction since it's a reactant. The PbSO4 is a product here and a product here. So odds are we're adding it. And then let's see here, the SO2, this is a product. We need to be a reactant, so we'll put a negative here. That will flip this reaction around. The only thing that remains here is the O2. And so what we're going to have to hope is that when we add and subtract these reactions, we've got the right coefficients to get the oxygens on the correct side. So we've got one lead here, one lead here. So we're going to add this reaction once. One sulfate here, one sulfate here. So we're going to subtract it once. One sulfate, lead 2 sulfate. So we're going to add it. And if we work it out, this negative actually makes this reaction SO2 goes to S plus O2. That will cancel out one of our oxygens. That'll cancel out the sulfur. Excuse me. And the lead sulfides here will cancel out. Something seems a bit off. Anyway, can't figure out what it is quite yet. But anyway, this is how you would do this. So now that you've figured out how you would have to add and subtract the reactions in order to get them to equal this, we would do the same things with the delta H's. So this is 1, 2, 3. So delta H1 plus delta H2 minus delta H3 would give you the delta H here. Now, you can do this. There is nothing inherently wrong with this, but again, this is not how it's done in practice. And when it comes to the exam, you'll actually, particularly for the big Hess's Law problem, you will have this option. So, stop it. So you can solve it by what I call method 1 and method 2 in the notes for the exam. And what on earth are you doing? So delta H1 is minus 96.6, delta H2 minus 923, delta H3 minus 296.8. So if I add the first two, subtract the last one, I get minus 722 kilojoules per mole. So that is the correct answer. What's the second method of doing this? The second method is to actually use the definition of Hess's law. So, where are you? Now, this is actually a relevant method, and we'll talk about it more in depth when we get done why you'd want to do this over the first method. But this is guaranteed to work assuming your reactions are set up correctly. So the definition of Hess's law is that the delta H of this reaction is the enthalpy of the products, in this case, lead 2 sulfide, minus the enthalpy of the reactants, lead and sulfur. And the H here refers to, see if I can afford space. This is the heat of formation at standard temperatures, delta HF naught. So heat of formation, the heat from making these from their elements at room temperature. So this statement's always true. It's dark enough for you to see on your screen. So all I've done here is I've just listed out Hess's law. Hess's law says that the sum of the enthalpy of the products times the reaction coefficients minus the sum of the reactants times the reaction coefficients will give you the delta H of reaction. It treats enthalpy as a conserved form of energy that's contained within the molecules. This is also true for Gibbs and entropy, and this is actually true. Like, they each contain their own enthalpy and their own Gibbs free energy and their own entropy. It's just that what those numbers are, quite frankly, are subjective. So we don't have a lower limit for Gibbs energy. We don't have a lower limit for enthalpy. We do have a lower limit for entropy. The delta S of a pure crystal is 0. So those are actual numbers, but as terms of H and G goes, it depends on what knot here is, what your reference is, and typically that's 25 degrees C in room and atmospheric pressure. So I know from this, delta H of this reaction is minus 96.6. I know from this, the delta H of this reaction is minus 923.1. Delta H of this reaction is minus 296.8. This is just the reaction I don't know. So I have a whole bunch of algebraic expressions that I can solve, and they never get harder than addition, subtraction, multiplication, and division. When I say multiplication, we're usually multiplying by a number, a constant. So what we can do is we can apply the definition. And the definition is that the heat of formation is the heat gained or lost by making any compound from its starting elements at room temperature. So for the heat delta H of formation of PB, that's 0 because the heat gained or lost by making lead from lead at room temperature is 0. You don't have to do anything, so there's no heat gained or lost. And this is true of sulfur as well, but PBS, we make that from taking lead and sulfur and combining it. There's definitely going to be heat gained or lost because we're making and breaking bonds in this case. So how do you know when it's 0? Well, if it's a pure element, it doesn't have a subscript unless it's a diatomic gas, we'll talk about it next, and it appears in its natural state. So lead is a solid at room temperature, that's going to have a heat of formation of 0. Sulfur at room temperature is a solid. It has a delta H of formation of 0. Diatomic gases are also 0, but they have to be diatomic gases. So the heat of formation of O2 from O2 at room temperature, that's 0. But the heat of formation of ozone, O3, is not 0 because oxygen doesn't naturally appear as ozone, O3 at room temperature. We have to use ultraviolet light. We have to supply energy. So go through the notes. It actually talks about what's considered 0 and what's not considered 0. The big hint that it's not 0 is that it's two elements bonded to each other. You definitely had heat gained or lost to make that happen. So PBS here does not have a 0 heat of formation. Here, lead 2 sulfate definitely has a non-zero. Lead 2 sulfide doesn't, but O2, diatomic gas, definitely has a 0 heat of formation. Down here, sulfur and oxygen are both 0, but SO2 is not. And down here, lead sulfate is non-zero, oxygen is 0, sulfate and lead 0, but the SO2, the sulfur dioxide, is not. So if we eliminate everything that has a 0, we're going to end up with a series of algebraic relationships. Now, all we have to do now is go through and start seeing where things equate. So here, the heat of formation of lead sulfide is minus 96.6 because we have the Hess's law relationship. Now here, we have lead sulfate minus lead 2 sulfide, but we can move that lead 2 sulfide over and get that the heat of formation of lead sulfate here is minus 923.1 plus the heat of formation of lead sulfide, which is minus 96.6. So when you solve this, you actually end up getting the heats of formation of things you may not have known before. So let me work that out. So I get that lead sulfate here is equal to minus 1019.7 kilojoules per mole. Now, sulfur dioxide, again, we just get this relationship that HSO2 equals minus 296.8. And so now if we substitute in, we get minus 1019.7 minus negative 296.8. And when I work that out, I should get the same number. Yep, minus 722.9. So again, these two methods should give you the same answer, but here's the big difference. With the first method, you only got the heat of formation of lead sulfate from this reaction. When you did this calculation here, not only did you pick up the heat of formation of this the heat of reaction here, you also picked up the heat of formation of sulfate, the heat of formation of lead 2 sulfide, and the heat of formation of lead 2 sulfate. These numbers are physical constants. So at room temperature, atmospheric pressure, That's the delta H of formation of those compounds. You can start building up a database, which we have done. So why is this the more useful method? Generally speaking, in the real world, we don't even bother with this. And I say this because I did these types of calculations a lot. Particularly when I was a postdoc at Stanford University, we would run these calculations because we need to know the free energy and the enthalpy release of a given reaction because we were trying to model and predict. So the only thing you would be given was this reaction here and asked to solve what's the delta H, what's the delta G. Well, that's super easy. You go look it up in a table of numbers and you have the same relationship we had before, delta H, heat formation of lead to sulfate minus heat of formation of lead plus heat of formation of SO2 plus the heat of formation of O2. And you can actually look these numbers up. You can go to the NIST-JANF tables. That's an open source, open resource from the Department of Energy. You can look up all these individual heats of formations and you can calculate it directly. There is no need to like go through all these different reactions. And there's going to be a question like this on the exam. But these are super easy ways to do these problems because the whole point of science is to build information. You don't have to start from scratch with these reactions and like rederive the heats of formations and add such reactions, subtract reactions. In fact, when I developed these problems, I had, what was it called? Why am I forgetting it now? Very expensive book I was able to borrow from Stanford University. And this book goes through, it's Barron, that's the name of the author is Barron. It's the compiling of all the NIST-JANF tables into a single book. So that's when I developed these problems, that's all I had to do was just look up the NIST-JANF tables and I could get all this information for free. So the way this differs for delta G is just numbers. You would do the exact same thing to find the delta G of this reaction. Now for the delta S, we don't ever compile entropies of formation. I mean, you can, they do exist in these tables, but they're kind of there to be there. The big thing we use is the Gibbs relationship. So if we've already solved this and this, delta S is just delta H minus delta G over temperature. And you've already worked out delta G and delta H. There's no point of having to go through the whole thing again with delta S. You can just rearrange this Gibbs relationship and get this answer. So again, you're going to see a problem just like this on the upcoming exam. Again, it can be solved by adding, subtracting, or using the Hess's law definitions to find delta H and delta G. And this is how you would squeeze out the delta S. But that's it for anything I wanted to discuss. Mostly I did this way I could start grading discussion boards. That's good to know. Mine is 722.9. So I've got the chat menu open. If you've got questions, please feel free to ask them. Otherwise, it looks like there's no one out there anyway. So So it looks like a lot of you getting the problem discussion board right. Let's run it from back. Hello, how's it going, Mohammed? I'm sorry, Mohammed. What's your question? I'm doing well, but keep in mind there's like a 1 minute lag between the video when you type, and it's just the latency issues. There's a trade-off with streaming. The better the quality of video, the bigger the lag between when I speak and when you hear it. But I can get it to like real-time conversations. The only cost is like there's going to be like no resolution on what you're saying. So these are not lectures; these are office hours. So this would be like any traditional office hour. So there's no prepared lectures because this isn't a lecture. If you're looking for videos on how to do things what is more akin to a traditional lecture, if you go to the course website under the lessons, under each lessons folder, there's a YouTube playlist. There's actually anywhere between 7 and 15 videos posted there. Those are actual lectures. But this is an asynchronous course. We don't offer lectures because if we offer lectures, we'd have to give a time, and there was actually an option given early first summer session where there were actually like online lectures. But because particularly with this course, we got people from Florida, Ohio, a lot of people from all around. We don't want to require there to be a set lecture time because they may not be able to make it. I mean, if you have questions, you're free to ask them. So these are very much office hours, and these are recorded with the idea that probably a lot of people have questions, and particularly if you can't make it to the live streams, you can always email in advance. You can say like, "Hey, I'm having a question about this. Would you mind answering it?" And I'll respond back saying like, "Yeah, I can definitely answer it." And I'll do it at the start, just so you don't have to sit through like an hour of video to get your question answered. Usually, all the emailed questions are answered first, and then any questions here in the chat, those get answered next, and go until I'm either out of questions or out of time. But yes, if you have questions right now, you're free to ask them. This is your time as an office hour. So if you were to show up in my office physically in campus and say, I've got a question, we would work through it. And this is just provided in case anybody wants to see how I work through that question or might have had a similar question. So the difference between an orbital and a wave function. Yeah, this is kind of where you're going to see, yeah, this is admittedly not. This is admittedly not well explained. So a wave function, by definition, we're going to use this probability. So that's your wave function. Is a probability. Probability distribution. When we're referring to electron density, but really, when it comes to wave functions, this is really referring to the mathematical description. So when we say a wave function, we're traditionally thinking about it in terms of a probability distribution of finding electron, but in general, the wave function can refer to any quantum phenomenon. So it is a mathematical function or mathematical description of a particular physical property. An orbital is a special case. It's the electron probability distribution. And it's actually represented by this function here, psi star. So we traditionally say that we square the wave function. That's not true. What we're doing is we're multiplying the wave function by its complex conjugate. So orbitals come about by taking a wave function and multiplying by its complex conjugate. So how are they related to quantum numbers? Where did you go? Looking for my eraser. Just have it. Did I do it? I'm definitely not doing this by hand. So I need just a minute to find my my eraser rag. Oh, that's unfortunate. I'm just going to do this by hand. Okay. So where do quantum numbers fit into this? So we have the Schrodinger wave equation, H psi equals E psi. And I really hate this representation. Really, H is a function. So H here, this is the Schrodinger wave equation, is your Hamiltonian. And E is your eigenvector. So an eigenvector is a given number, and all eigenvalue problems have the form that we have some function on our equation equals a number. Sorry, not your eigenvector, eigenvalue. So that's a function. That's a number. So this Schrodinger wave equation falls underneath a very specific class of eigenvalue problems, where H, Hamiltonian, is a function that describes energy. So it's a specific function that translates this wave function to the wave function times an energy. I really wish I could find my eraser. I really don't see where it would have gone in all of this. Okay, we're just going to have to use this. So what happens? So the simplest example we can give is what's called a particle in a box. So with a particle in a box, we have some electron constrained between two walls. At the walls, there is infinite energy. So the y-axis here is energy, and it's infinite energy between either side. And we have two restraints. The probability of finding the electron has to equal 1 inside this entire box. And 2, the probability of finding the electron, we can call this a 0 to L, at 0 and the wall is 0. So there's no chance that you're going to find this electron at the walls because the walls have infinite energy. So we can conceive of a lot of solutions to this. There's one solution that looks like this. There's that. And so forth. So we end up getting these sine waves. The problem is that we get an infinite number of solutions to this. So this is where your quantum numbers come from. So your quantum numbers are what are called eigenvectors. And they basically tell you which solution you're working with. So there are four principal quantum numbers: n, l, m sub l, and m sub s. And these four quantum numbers uniquely tell you which wave function corresponds to that particular electron density. Yeah, you're welcome. So the first number, big N, is what's called the principal quantum number. And the best way to think about it is this is the address of the electron. The N sets the energy the most. So the N sets the lower limits for the energy. So N is principal. And what it sets is the number of radial nodes. So N can be 1, 2, 3, 4, and so forth. And the radial nodes is just N minus 1. Next up is the angular momentum. And L is between why am I remembering this wrong? So L can take any value 0 to n minus 1. There we go. And it can be any integer value. So if n equals 1, L equals 0. If n equals 2, L equals 0 or 1. If n equals 3, L equals 0, 1, 2, and so forth. And this is just a consequence of solving the full-on Schrodinger wave equation. Now, L is going to give us a lot of information, but it describes the big thing is it describes the degeneracy. So the degeneracy is basically how many different solutions of N and L are unique. So if L equals 0, we only have one configuration. If we have L equals 1, then there are 3 possibilities for orientation. L equals 2, there are 5. L equals 3, there's 7. So what do I mean? This is also reflecting the symmetry. So if L equals 0, we have S symmetry. L equals 1, we have P symmetry. L equals 2, we have D symmetry. L equals 3, we have F symmetry. So S symmetry, the only one that actually seems to be intuitively named, S is spherical symmetry. There is only one way to orient a sphere in space uniquely. L equals 1, there are 3 ways. So if we look at the P orbital, so an S orbital is a sphere. When it comes to a P orbital, we actually have 3 ways we can orient it and not see a difference. On the z-axis, on the x-axis, and the y-axis. D is going to take the same way. There are 5 different ways to orient this and get the exact same answer for an atom sitting in space. But because of this degeneracy, this is where we get the M sub L number. So the M sub L number tells you which of these solutions you're working with. So M sub L is between L and negative L. So in this case, M sub L equals 0. There's only one choice. Here, M sub L could equal negative 1, 0, and 1. When we get to D, we get negative 2, negative 1, 0, 1, and 2. So basically, M sub L tells you which of these atomic orbitals you're in. The last one is M sub S. This is electron spin. This takes a value of 1/2 and negative 1/2. Spin up, well, spin up and spin down is the wrong way to think about it. It's alpha spin and beta spins are the better way to think about it. But basically, spin just describes the angular momentum of the electron. It pretends like it's spinning on a top. And a spinning top can orient both clockwise and counterclockwise. Electron spin is the same way. It can be clockwise or counterclockwise. For an electron by itself, it's spin 1/2. For two electrons paired up, the second electron takes a -1/2 spin. And all that means is that they're spinning in opposite directions. It doesn't tell you if it's up or down. There's a big fundamental reason for that. So, we're ready to talk about atomic orbitals now. So with all of that in mind, I realize this is a very rushed explanation. If we look at our principal quantum numbers, 1, 2, 3, 4, 5, and values of L. So we have 0, 1, 2, 3, 4, 5. For n equals 1, there's only one option for L, and that's 0. For n equals 2, there's two possibilities. There's 2s and 2p. But L has to be less than or equal to n minus 1. For 3, we have 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and there are actually 5g orbitals that are so high in energy they're not particularly accessible. And so that's where these atomic orbitals come from. You've got n equals 1, L equals 0. For your p orbitals, you've got three choices. You've got n equals 1, L equals 1, but then you have ml equals -1, 0, and 1. So this would be like a px, a py, and a pz. For 3d, n equals 3, L equals 2, and ml can be -2, -1, 0, 1, and 2. This would be your dxy, dxz, dyz, dz squared, and dx squared minus y squared. These, again, are kind of arbitrary definitions. Yeah, you're welcome. And you're free to, like, play this video and share it. Like, I really don't mind sharing these live streams with anyone. So these definitions, dxy, dxz, they don't necessarily correspond to these mLs. These are arbitrary assignments. They don't begin to matter until the atom gets exposed to things. So this is how your quantum numbers fall out of it. This is where your atomic numbers come from it. And the weird thing is that you're going to do all this work. The actual shape you observe, so your psi is going to have these four numbers, n, l, ml, ms. The actual shape you see, this 2s, is multiplying the wave function by its complex conjugate. And that's where we get these 3D projections from. So yeah, I know that's a lot of information to take. This is actually something I would prefer would be covered at a graduate level because we don't require calculus. And most courses don't require calculus for Chem 1, Chem 2. It's a real shame. But that said, I wasn't until I got into graduate school and actually started covering what are called Sturm-Liouville systems. And they're a special class of eigenvalue, eigenvector problems. So again, they're going to kind of take this f y of x equals e y of x, where x is a three-dimensional vector. They'll start taking this form, and that's where you begin to crash into this, like, well, e has its own values, has its own eigenvectors. Y is going to have its own eigenvectors. And your quantum numbers are just saying which energy corresponds to which particular set of quantum numbers. It's a lot more than you would need to know at like the Chem 1 level, though. All right. Thank you for showing up, and we're coming up 11 o'clock, so go ahead and sign off now. Thanks for coming, Mohammed. Live streams are Mondays and Wednesdays 10 to 11 and 11 to 12 Tuesdays and Thursdays. You're free to come by, ask questions. I'm going to give priority to students currently taking my Chem 2 course, but again, you're free to ask questions, particularly if there's no one here. Ask away. All right, thanks for coming, and I will see y'all tomorrow.